Late autumn, 1944. Somewhere near the Lorraine border, a German forward observer wiped the cold condensation from his binoculars and stared down at a muddy secondary road. It had to be hauled away by specialized heavy recovery vehicles, loaded onto a rail car, and sent back to a major rear echelon depot. The mechanic knew that the exact same bolt, cut with the exact same standardized thread pitch, was holding together the chassis of a wrecked cargo vehicle, sitting 50 yards away. By utilizing identical fasteners, a mechanic only needed a small, standardized toolkit to strip down a massive variety of machinery. The shattered truck was no longer just battlefield debris, it was a perfectly catalogued parts donor for the tank. By eliminating the physical friction of fitting components, the Americans turned combat repair into a high-speed assembly line, a destroyed transmission that would take a German master mechanic a week to carefully rebuild. And hand-fit could be entirely swapped out by 3 exhausted American teenagers with a heavy hoist in an afternoon. They rarely wasted time fixing broken, internal gears under enemy fire. They simply unbolted the entire ruined module, tossed it into the salvage pile, and bolted in a pristine replacement. This drop-in capability was the real reason the German observer on the hill had watched a dead armored column return to life in 48 hours. The Americans were not repairing machines in the traditional European sense. They were rapidly reassembling them. Yet, enforcing this level of absolute physical conformity was a monumental task. The American military did not build its own vehicles. It relied on civilian manufacturing corporations, fierce commercial rivals who had spent decades guarding their own proprietary designs, unique tool sizes, and private patents. To guarantee that a Ford component would fit flawlessly, their highly trained engineers would spend weeks diagnosing the damage and waiting for custom parts. Yet, as the freezing rain into a Chrysler tank in the middle of a European winter, the government first had to force an unprecedented compromise. To understand how a teenage mechanic could perfectly align a heavy steel gear in the freezing rain of Lorraine, you have to look back 3 years and 4,000 miles to the deafening assembly floors of Detroit. Before the war, the American automotive industry was a fiercely guarded ecosystem of commercial secrets. General Motors, Ford, and Chrysler were bitter rivals. They protected their proprietary patents, unique thread pitches, specialized tool sizes, and exclusive engineering standards. In peacetime, locking a customer into a proprietary ecosystem was a massive commercial advantage. In a global, mechanized war, it was a fatal liability. The United States Ordnance Department understood that sending a fractured, proprietary fleet of vehicles across the Atlantic would guarantee a logistical collapse. If a frontline tank battalion needed a replacement water pump, the supply chain could not pause to figure out whether that specific engine was manufactured by Ford or Continental Motors. The military issued a radical mandate. The era of the bespoke, proprietary vehicle was completely suspended. The government demanded that fierce commercial competitors share classified blueprints. Combined production lines continued to fall. On the third morning, the observer heard the unmistakable, high-pitched whine of radial engines and the heavy clatter of steel treads, and adopt an uncompromising set of universal engineering tolerances. This was the Detroit Compromise. Working alongside organizations like the Society of Automotive Engineers, the military forced rival executives to agree on a single, standardized reality. They synchronized thread counts on fasteners, so a wrench from a civilian hardware catalog could turn a bolt on a 30-ton tank. They agreed on standardized metal alloys, universal wire gauges, and identical hydraulic pressures. If an independent foundry in Ohio cast a heavy steel road wheel and a rail car delivered it to an assembly plant in Michigan, It had to slide flawlessly onto an axle built in Indiana. There was no time for final adjustments on the line. Achieving this scale of interchangeability required a deliberate tactical sacrifice. The Ordnance Department willingly traded peak bespoke performance for absolute, unyielding uniformity. When German engineers designed a combat vehicle, they constantly pushed the boundaries of metallurgical science to create heavy, complex machines like the Panther and the Tiger. Those vehicles often boasted superior armor and highly tuned engines, but their tight, overlapping road wheels and custom internal layouts were impossible to mass-produce with standardized civilian labor. The Americans actively rejected the masterpiece. The column was coming back. Through the magnified glass of his optics, the German soldier looked for the telltale signs of fresh reinforcements. They designed the M4 Sherman and the standard cargo truck to be manufactured by civilian factory workers, not master machinists. They simplified internal geometries. They widened mechanical clearances just enough to prevent battlefield mud from locking up the machinery, while keeping the manufacturing tolerances strict enough that any replacement part would drop cleanly into any hull. They built machines that were not designed to be physically invincible on the front line, but rather infinitely repairable immediately behind it. The industrial discipline held. By 1943, an unprecedented volume of perfectly interchangeable components was flowing out of the American Midwest. Millions of identical pistons, standardized bearings, and uniform suspension springs were packed tightly into wooden crates and loaded onto eastbound freight trains. But manufacturing an interchangeable part in a well-lit Michigan factory was only the first step. The true test was whether this rigid organizational logic could survive. Being packed deep in the holds of Liberty ships, hunted by enemy submarines, dragged onto shattered European beaches, and distributed to thousands of isolated combat units under heavy artillery fire. The system had conquered the factory floor, but now it had to survive the brutal mathematics of global logistics. Deep in the hull of a Liberty ship crossing the winter Atlantic, the mathematics of a global mechanized war were finally being tested. He expected to see pristine paint, untouched armor, and entirely different unit markings, indicating a new battalion. If the United States had adopted the European doctrine of bespoke engineering, that cargo hold would have been a logistical nightmare. It would have been packed with 10,000 highly specific, custom-machined parts. Quartermasters in Washington would have been forced to guess exactly which specific variant of which tank might break down in France 3 months in the future. A wrong guess meant a supply depot sitting on tons of useless steel, while frontline armored battalions bled to death waiting for parts. Standardization eliminated this guessing game, because the Ordnance Department had forced the Detroit factories to use identical base components. The global supply catalog collapsed in complexity while exploding in raw volume. The cargo manifests did not list hundreds of unique transmission gears for a dozen different chassis variants. They listed massive, standardized crates of universal bearings, identical spark plugs, and modular fuel pumps. These pallets did not have to wait for one specific vehicle to take damage. They could be instantly routed to an artillery tractor, a cargo truck, or a Sherman tank. The math was brutally efficient. The military carried fewer types of parts, but carried inexhaustible volumes of the components that broke most often. Yet, even the most efficient transoceanic supply chain could fracture under the friction of war. German submarines sank freighters. Heavy rains washed out rail lines. A rapid armored advance could stretch lines of communication so thin that forward maintenance battalions were completely cut off from rear depots. Instead, he saw the exact same vehicles. He recognized the specific tactical codes stenciled on the olive-drab hulls. During those critical, desperate windows, the American system relied on its most ruthless and effective logistical weapon. It was called controlled cannibalization. In the Wehrmacht, a heavily damaged vehicle was a liability that had to be carefully evacuated to a specialized factory for rebuilding. In the American Army, a shattered vehicle instantly became a forward supply dump. If a Sherman tank hit a heavy anti-tank mine and suffered catastrophic, unrepairable structural damage to its lower hull, the maintenance crew did not simply abandon the wreck, because they knew every single internal component was universally compatible. The ruined tank was immediately harvested. Working under the cold rain with heavy canvas slings and A-frame hoists, grease-covered mechanics would strip the dead machine to the bone. They pulled its starter motor, unbolted its undamaged road wheels, detached its carburetors, and salvaged its unbent track links. A single destroyed tank could instantly provide the exact drop-in replacement parts to heal 3 other damaged vehicles. The mechanic in the forward tent never had to worry that the alternator pulled from a burned-out wreck was secretly incompatible with the engine he was trying to fix. The math of interchangeability guaranteed the fit. If an artillery shell destroyed a heavy truck, the surviving crew could harvest identical axles, high-tensile fasteners, and universal joints to keep a half-dozen other cargo trucks moving forward. The battlefield itself became a perfectly indexed warehouse, filled with pre-machined donor organs. He could see fresh, jagged weld marks, scorched armor plating, and oddly clean replacement wheels hastily bolted onto the battered Shermans. By standardizing the cargo across the ocean and turning every wrecked machine into a guaranteed donor, the Ordnance Department prevented the transatlantic supply chain from collapsing under its own massive weight. The theoretical system of the assembly line had survived the journey to the front line, but peacetime planning and logistical math only proved the system could function on paper. The true measure of the system, machinery, was what happened when it was pushed to its absolute breaking point under maximum combat pressure. Summer of 1944. The Bocage country of Normandy was a claustrophobic labyrinth of ancient, high earthen banks and thick hedges. For American armored units pushing into this terrain, it was a mechanical meat grinder. Concealed German anti-tank guns and infantry armed with magnetic mines engaged at point-blank range. The initial losses were staggering. To a German battalion commander reading the daily after-action reports, the tactical math was clear. They were bleeding the American armored spearheads dry. By their calculations, entire enemy divisions should have been rendered permanently combat ineffective within a matter of weeks. Instead, the American lines only grew heavier. The German commanders were calculating attrition based on their own logistical limitations. They did not know that just a few miles behind the front, hidden beneath camouflage netting and within earshot of the artillery, he saw the same cargo trucks, heavily loaded with artillery ammunition, rolling smoothly over the uneven ground despite having the United States Ordnance Maintenance Battalions had established sprawling outdoor factories. When an American Sherman was immobilized in the hedgerows, it was not left to rust in the ditch. Heavy armored recovery vehicles hooked onto the shattered hulls and dragged them rapidly back to these muddy depots. Here, the mathematical theory of interchangeability became a brutal operational reality. The maintenance companies operated on a continuous shift, functioning exactly like a Detroit assembly line dropped into a combat zone. If a tank arrived with a destroyed radial engine, the mechanics did not open the block to carefully repair shattered pistons. A heavy crane simply lifted the entire ruined engine module out of the chassis. A wooden crate from a depot ship was pried open. A pristine, standardized replacement engine was lowered into the empty bay. Because the mounting bolts, fuel lines, and electrical connections were universally identical, the heavy machinery slid perfectly into place. The tank rolled back toward the front lines in a matter of hours, often returning to the exact same combat sector. This modular approach allowed the American military to absorb punishment that would have destroyed any other army. During the campaign in Western Europe, some American armored divisions suffered equipment casualty rates exceeding 100%. They technically lost their entire starting inventory of vehicles over months of fighting, their suspensions entirely crushed just 48 hours prior. It made absolutely no sense. The Americans had not brought up a fresh, yet they never stopped advancing. A Sherman knocked out on a Tuesday could be gutted, refitted with standardized donor parts harvested from a wrecked cargo truck, and returned to the offensive on a Thursday. Across the line, German panzer divisions suffering identical damage were paralyzed. When a German tank took a devastating hit to its transmission, it often sat idle in a rear area depot for weeks. The master mechanics were trapped waiting for a highly specific replacement part that was stalled in a bombed-out rail network somewhere deep in Germany. Even if the part arrived, the time spent hand-fitting and machining the component meant the vehicle was useless during the critical days of a battle. The German army was fighting a traditional war of arithmetic, counting destroyed hulls and assuming they were winning. The American army was fighting a war of velocity, circulating interchangeable parts faster than the enemy could destroy the vehicles holding them. The operational advantage was overwhelming. The speed of the American repair system meant that a local tactical defeat could be almost entirely erased by the next morning. The machinery of war had been decisively decoupled from the slow, artisan traditions of Europe. But as the freezing rain continued to fall over the battlefields of late 1944, a deeper question remained. As the German forward observers watched the exact same vehicles return to the front line, did they ever realize that the true weapon, armored unit from the rear, they had resurrected the dead one? To the German defenders, this defied the laws of mechanical physics. Defeating them was not the steel of the tank itself, but the invisible system of standardized logistics operating just out of sight. On the Lorraine border, the German forward observer slowly lowered his binoculars, the cold rain washing over the steel of his helmet. Down in the valley, the high-pitched whine of radial engines and the heavy clatter of steel treads echoed as the resurrected American column pushed steadily past the exact ambush site that had supposedly destroyed them. He had assumed the smoking hulls left in the ditch 2 days earlier were permanent casualties, tactical victories permanently checked off in a ledger. He believed the rules of industrial warfare were fixed and universal. A broken machine required a master craftsman, a factory blueprint, and weeks of unyielding time. What the observer could not see through his optics was the massive, invisible machinery operating just behind the tree line. He did not know about the heavy canvas manuals of the standard nomenclature list, translating chaos into a simple string of digits. He could not see the standardized threads on the high tensile bolts, the identical bearings shared between a 30-ton tank and a battered cargo truck, or the modular engine blocks shipped across the Atlantic. He believed his anti-tank guns had permanently eliminated a mechanized threat. 2 days earlier, this exact stretch of terrain had been a mechanized slaughterhouse. An American armored column had pushed too far forward. They knew intimately what it took to fix a broken machine of war. In their own ranks, repairing a damaged Panzer IV or he did not realize his shells were merely initiating a high-speed, drop-in replacement cycle that the American military had perfected before the war even began. The question of the mechanized war was never really about whose factory could forge the thickest frontal armor, or whose engineers could design the most mathematically perfect gun sight. It was about what happened after the metal inevitably broke. The German military built bespoke masterpieces, designed to dominate the battlefield only when they were functioning perfectly. But in doing so, they created a brittle force. When their masterpieces broke, the entire system paralyzed itself, waiting for a custom cure. The American military designed an entire logistical ecosystem to survive the absolute certainty of failure. They accepted that tanks would burn, suspensions would shatter, and heavy axles would snap in the mud. Instead of trying to prevent the damage, they built a system of standardized interchangeability that cured the damage faster than the enemy could inflict it. But a system of interchangeable parts is only a theoretical idea until human hands put it into motion. The standardization of the American war machine was not executed by generals pointing at strategic maps or automotive executives sitting in warm Detroit boardrooms. It was enforced by 19- and 20-year-old men standing ankle-deep in the freezing mud of Western Europe. Heavy tank was an artisan craft. It required a master mechanic, precise factory-specific replacement components, and the time to painstakingly. It was the mechanics, the heavy recovery crews, the welders, and the supply clerks. These were young men who had learned their trade fixing civilian tractors and delivery trucks, suddenly tasked with keeping a global war moving forward while under the constant threat of enemy artillery. They did not wear pristine uniforms, and they rarely received medals for gallantry. They lived in rain-soaked canvas repair tents, their skin permanently stained with motor oil, freezing hydraulic fluid, and the harsh, metallic smell of solvent. They worked through the freezing nights with flashlights clamped in their teeth, operating heavy chain hoists to rip ruined iron out of shattered hulls. To the German army watching from the ridge, the returning tanks looked like a tactical impossibility, a mechanical miracle that defied the laws of war. But there was no miracle in the mud of Lorraine. There was only a canvas book of numbers, a wooden crate full of identical steel parts, and an exhausted, grease-covered teenager holding a wrench, turning a bolt that fit perfectly on the very first try. Hand-fit those pieces using metal files and portable lathes. The engineering tolerances were incredibly tight. A shattered transmission gear meant waiting weeks for a requisitioned replacement that matched the exact factory production run of that specific chassis. What the observer was seeing on that muddy road was a physical impossibility. There were no heavy industrial rail yards or manufacturing plants within miles. There were only cold fields, canvas tents, and exhausted men in grease-stained coveralls working in the freezing mud. The German military believed they were fighting a standard war of industrial attrition, where breaking an enemy tank meant it was removed from the chessboard for a month. They could not comprehend that they were actually fighting an enemy who had entirely rewritten the rules of how heavy machinery was built, broken, and healed. To understand how an American armored force could absorb devastating physical losses and simply roll the exact same vehicles back into combat the next morning, we first have to understand rolling right into a dialed-in anti-tank ambush. The observer had watched the high-velocity shells do their work, the rigid artisan trap of the German engineering system, and why the men behind the anti-tank guns were so certain that a broken machine was a dead one. To the German observer watching the resurrected American column, a tank was not merely a weapon. It was a piece of high-precision engineering, crafted in a culture that venerated the artisan mechanic. Throughout the 1930s and deep into the war, German manufacturing relied on a philosophy of constant, bespoke refinement. When a major industrial firm designed a vehicle, they built it like a finely tailored suit. This meant that German heavy machinery was often brilliant, but it was also fluid. If an engineer discovered a slight improvement for a transmission gear or a suspension housing midway through a production run, the factory immediately implemented the change. The result was a dizzying array of vehicle variants. A mid-war Panzer IV had different variants that were fundamentally incompatible with each other, and an early production heavy tank possessed internal components that would never fit a late production model. On paper, continuous improvement sounded like a tactical advantage. In the freezing mud of a combat zone, it was a logistical nightmare. When a German tank took a high-velocity hit that shattered its drive sprocket, the recovery crew faced an immediate identification crisis. The mechanic could not simply order a generic replacement part. He had seen the 30-ton Sherman tanks violently throw their heavy steel tracks, their suspension bogies shattered. He had to know the exact factory block, the production month, and the specific chassis variant. If the supply train actually managed to deliver a replacement, the friction only increased. Because European factories relied heavily on hand tooling and tight, custom tolerances, 2 parts stamped with the exact same serial number might still differ by fractions of a millimeter. When the replacement arrived at the field workshop, it rarely fit perfectly on the first try. The mechanic had to become a machinist. Under the dim light of a canvas tent, he would use a heavy metal file, a micrometer, and a portable lathe to shave down the steel, manually forcing the new component to mate with the damaged hull. This was the artisan's trap. The Wehrmacht had engineered vehicles that demanded master craftsmen to maintain them. Every repair was a custom job. The sheer volume of unique, specialized parts meant supply depots were overwhelmed with mismatched inventory. A maintenance unit might be surrounded by crates of engine valves and track pins, yet find themselves completely paralyzed because none of those specific pieces fit the exact variant of the broken machine sitting in front of them. This doctrine of bespoke engineering formed the entire worldview of the observer on the Lorraine border. He knew that if his own unit had suffered shattered axles and cracked engine decks, the vehicles would have been dragged away to wait, their engine decks smoking from internal damage. He had watched the accompanying 2.5-ton supply trucks rupture their drive axles for specialized parts and custom machining. He calculated the American recovery time based on his own army's limitations. He was wrong because he assumed the enemy built machines the exact same way. The American military had realized before the war that a vehicle requiring a lathe to repair in the field was a vehicle that would inevitably be abandoned. To sustain a mechanized war across thousands of miles of ocean, they had to eliminate the cognitive friction of identifying parts. The secret to how that shattered column returned to the road so quickly began not with a wrench, but with a massive, standardized catalog that spoke a universal language. Inside a canvas repair tent, miles behind the front line, an American mechanic stood over the ruined suspension of a 30-ton Sherman tank. The temperature hovered near freezing, and the floor of the tent was deep, churned mud. He was 20 years old. 2 years earlier, he had likely been repairing tractors in Ohio or working at a civilian gas station. He was not a master machinist. He did not own a precision micrometer, and he had no access to a heavy metal lathe. When he looked at the jagged, sheared steel of a broken suspension bogie, he did not attempt to reverse engineer the damage or calculate custom tolerances, and collapse helplessly into the deep ditches. In the grim tactical mathematics of the Wehrmacht, that column was dead. He simply wiped his grease-covered hands on his coveralls, stepped away from the machine, and opened a thick, canvas-bound book. This was the standard nomenclature list, classified by the Ordnance Department under a vast series of alphanumeric codes. To an outsider, it was a heavy, aggressively dull collection of exploded line drawings and endless columns of text. To the American mechanized war effort, it was the universal language that bypassed the chaos of combat. When the young mechanic examined the shattered suspension, he simply found the corresponding diagram in the manual. Every single nut, bolt, spring, bearing, and housing on the vehicle had a designated line pointing to a specific, standardized part number. He did not need to know what month the tank was built. He did not need to check if the factory in America had tweaked the design midway through the year. He traced the diagram, found the code for the broken component, wrote it on a requisition slip, and handed it to a unit clerk. This manual entirely eliminated cognitive friction from the battlefield. In the European tradition, ordering a replacement part often required a complex technical conversation. It required describing the specific chassis variant, the modification block, and hoping the rear echelon supply officer understood the nuance. The surviving American crews had retreated under fire, leaving their broken machinery bogged down in the mud. In the American system, the mechanic transmitted a single string of standardized digits over a crackling field radio. That exact string of digits was stenciled onto a wooden crate sitting in a massive rain-soaked supply dump in northern France. It was printed on the manifest of a cargo ship crossing the Atlantic Ocean. It was stamped on the shipping crate at an assembly plant in Detroit. There was no translation needed. A supply clerk who had never seen a Sherman tank in person could pull the exact required component from a mountain of inventory simply by matching the numbers. Even more crucially, the manual was radically cross-referenced. If the mechanic needed a specific high-tensile bolt or a standard ball bearing to secure a drive shaft, and the supply depot was delayed by enemy fire, the book provided an immediate tactical alternative. The manual revealed everywhere else that component lived. It showed that the exact same standardized bolt was used in the mounting bracket of a common 2.5-ton transport truck, or the carriage of a towed artillery piece. If the mechanic needed that part immediately, he walked over to an unrecoverable truck sitting in the unit's scrap pile, unbolted the piece, and knew with absolute certainty that it was identical. The American military recognized that time spent trying to identify. By every rule of war the German army understood, a mobility kill was a permanent battlefield elimination. A mechanical problem was time the vehicle spent dead. By replacing the master craftsman with an exploded diagram and a universal numbering system, a teenager in a freezing tent could diagnose a mobility kill and order a replacement in minutes. But a universal catalog only solves the friction of identification. A serial number can guarantee that the correct box arrives at the repair depot. It cannot force a heavy piece of cast steel to securely mate with a damaged hull. Knowing what a part was called was useless if the mechanic still had to spend hours filing it down to make it fit. The true test of the system was not on the page, but in the physical metal itself. When the supply clerk handed the wooden crate to the mechanic in the freezing mud of Lorraine, the true advantage of the American system was finally unlocked. The mechanic pried open the lid and lifted out a heavy steel transmission gear. He did not carry it over to a portable lathe. He did not measure it with a micrometer to check for microscopic variations. He simply carried the cold steel over to the shattered hull of the Sherman tank, aligned it with the housing, and slid it into place. It fit perfectly on the very first attempt. The bolt holes aligned exactly. The gear teeth meshed seamlessly. With the aggressive turn of a standardized wrench, the installation was complete. This was the anatomy of absolute interchangeability. A tank with a blown transmission or a destroyed drive sprocket could not simply be patched up in the rain. In the American military doctrine, a replacement part was not a rough draft waiting to be customized. It was a finished product, engineered to a drop-in fit. The United States Ordnance Department had stripped the burden of precision away from the soldier in the field and pushed it entirely onto the factory floor, thousands of miles away. If a component required hand filing or custom machining to fit a vehicle in a combat zone, it was considered a severe failure of manufacturing, not a normal step in maintenance. But the design philosophy went far deeper than simply making sure one Sherman tank part fit another Sherman. The military engineered interchangeability across entirely different classes of vehicles. They achieved this by building their vast mechanized army around a shared library of standardized base components. If a heavy ordnance truck took shrapnel to its engine bay, a mechanic did not necessarily need Sexidine base to wait for a truck-specific shipment. He could look at the M4 Sherman, the M3 half-track, or a mobile artillery carriage and recognize shared automotive DNA. Spark plugs, carburetors, fuel pumps, and electrical relays were deliberately standardized across different platforms. The heavy steel bearings on a supply trailer might match the bearings on a prime mover. A single type of standardized automotive battery-powered jeeps, transport trucks, and armored cars alike. This meant that an American repair depot was rarely paralyzed by a lack of highly specific, bespoke components. If a unit was missing a specialized high-tensile bolt to secure a tank suspension,